Welcome to my presentation on the gas laws. I'm Bernard Taylor and this is Phys Physics. And of course, keep working and persevere. Learning stamina is important, particularly in these difficult times. And you will hopefully move forward even when mistakes are being made. In the words of the late, great Leonard Cohen, forget your perfect offering. There's a crack in everything. That's how the light gets in. So keep bringing light into your life, keep working hard. Now, some years ago, I was able to peruse Robert Boyle's collected works, and they're a fascinating collection of works. Although some of the experiments involving birds and mice and the newly invented vacuum pump wouldn't get through a university ethics committee today. Indeed, up on the right-hand corner, you see the vacuum pump that was developed by Robert Boyle and indeed Robert Hooke, he of Hooke's law. And let's just look at these words of Robert Boyle. Of the structure of the elastical particles of the air, diverse conceptions may be framed, for one may think them to be like the springs of watches, coiled up and still endeavouring to fly abroad. And so on. And what is Hooke doing? Well, he's trying to develop ideas, models to explain air before atoms and molecules were fully understood. Now, here we have a mercury barometer showing how a mercury barometer is made from a tube, an inverted tube, put into a dish of mercury. And what do we have? We have the pressure of the atmosphere on the mercury in the dish balancing the force, the pressure exerted by the 750 millimeters of mercury. Of course, these days, we wouldn't be allowed to use mercury in a school or a college like this because it's dangerous. So what has this got to do with Boyle's law? Whose law? Well, in many countries, in Europe, it's known as the Boyle-Mariotte law. And indeed, it wasn't known as Boyle's law, even by Boyle himself. Well, there was a gentleman scientist called Robert Towneley, living in Lancashire, who constructed a mercury barometer, something like this, and we can imagine that there was some trapped air in the column of mercury. He took this up Pendle Hill in Lancashire, and at the top of the hill, there'd have been lower atmospheric pressure, so there would have been a larger volume of trapped air. Coming down the hill, there would have been a higher atmospheric pressure, so a smaller volume of trapped air. And Boyle refers to this result, because Robert Towneley was in correspondence with Boyle. Boyle refers to it as Mr. Towneley's hypothesis. We're more familiar with this kind of apparatus in schools and colleges to explain what we now call Boyle's law. In this apparatus, pressure is put onto the trapped air above the oil using this car pump along with a pressure gauge. We've got a scale to measure the volume. So typically the pressure is increased to a maximum value and the volume of the trapped air decreases. So far so good. The valve is closed and the pump can be removed. The pressure on the trapped air is decreased slowly in stages by opening the valve. Each time, readings are taken of pressure and volume. The pressure release is slow so as not to change the temperature of the trapped air. And what do we find? Well, pressure is inversely proportional to volume. And pressure equals some constant times 1 over V. And typically, we get a graph of pressure against volume, which I've sketched on the right-hand side. increase the pressure, we decrease the volume, and vice versa. So pressure times volume is a constant, provided the temperature remains constant. And I'm emphasizing that yet again. So increase the pressure, decrease the volume. But how do we explain this in terms of particles and collisions? Well, as the volume decreases, there'll be many more collisions per second between the gas molecules and the walls of the container. Overall, a greater rate of change of momentum, a greater average force on the walls of the container, and a greater pressure. Okay. And what do we have here? Well, we're beginning to look at the pressure law. We've got a glass flask, sealed apart from the pressure gauge. It's in a water bath and it's heated, perhaps by a Bunsen burner. But this doesn't look really complete or indeed really safe. Perhaps you can think of some things that could be done to clarify this, indeed to improve it. Yes, no thermometer is shown. Perhaps more of the flask should be in the water. We need a safety screen. And it would be better to have a safety valve like a pressure cooker. So what happens? If we increase the pressure, sorry, I've got that the wrong way around. If we increase the temperature, we increase the pressure, of course. And we find that the pressure is directly proportional to the absolute temperature, the temperature in Kelvin. But how do we explain this in terms of particles and collisions? Well, as the temperature increases, the molecules will be moving faster, so there'll be many more collisions per second between the gas molecules and the walls of the flask, the glass flask. Overall, there'll be a greater rate of change of momentum, a greater average force, and so a greater pressure. And if we were to sketch this graph, well, we might be able to get a few data points between 0 degrees centigrade, which is 273 Kelvin, of course, and 100 degrees centigrade or slightly above, because this will be under pressure. But then we dot backwards. Dotting backwards, we extrapolate backwards. And if we're lucky, we'll get a really quite a decent value for absolute zero. So pressure is directly proportional to the absolute temperature. Increase the temperature and we increase the pressure, but we're keeping the volume the same. Now, Charles' law, what is this about? Well, volume is directly proportional to the absolute temperature. If we increase the temperature of a gas, we increase its volume, provided the pressure remains constant. And how do we explain this in terms of particles and collisions? Well, if we have the temperature being increased, the molecules are moving faster, we have many more collisions per second with the walls of the container and indeed with the piston, and only the piston can move. So there's a greater rate of change of momentum or a greater average force, and the piston will move to increase the volume. And you may remember my experiment with a sealed plastic syringe. Sealed at one end, there's a constant pressure on the barrel of the piston. And so if the temperature increases, the volume increases. So Charles' law, to repeat, at constant pressure, volume is directly proportional to the absolute temperature. Increase the temperature and we increase the volume. So 3 gas laws. Let's just look at them. Boyle's law, Charles' law, the pressure law. And we can combine them so that P times V over T equals a constant. And many of you who've worked with the gas laws, perhaps in chemistry or perhaps previously in physics, will know what's coming next. PV over T is some constant, so P times V over T, that's a constant, that will equal P naught times V naught over T naught. Okay, we might call this P1 V1 over T1 equals P2 V2 over T2. It doesn't really matter. But if we deal with 1 mole of a gas, then T naught, the temperature, is 273 Kelvin. V naught, 0.0224 cubic meters. And the pressure, we're talking, of course, about standard temperature and pressure, is 101 kilopascals. And P naught, V naught equals NK T naught. This is one of the basic equations that we'll be looking at when it comes to the kinetic theory of gases. But P naught V naught equals NK T naught. And just looking down to the bottom of the page, N is the number of molecules and K is what we call the Boltzmann constant. We can rearrange that equation to get a value for K. K equals P naught V naught over N times T naught. I put those values in and I get a value for the Boltzmann constant, 1.38 times 10 to the minus 23 joules Kelvin to the minus 1. But that will be found in your data booklet. What I do want to emphasize here is that, yes, we have P1 V1 over T1 equals P2 V2 over T2, but also P times V equals NKT. In chemistry, we very often find PV equals nRT, where N is the number of moles and R is the molar gas constant. Hey, I'm not going to use that in what follows. That's more to do with chemistry. So I'm reiterating that the gas laws can be combined, and this leads to PV equals NKT for an ideal gas. Now, what do we mean by an ideal gas? Well, we explore this a little bit more when we talk about the kinetic theory of gases. But Maxwell and Boltzmann developed our modern understanding of gases and developed a number of equations which are mathematical models based on certain assumptions. These models assume an idealized version of a gas, that there are large numbers of particles present in a gas. The particles collide frequently, indeed with each other and with the walls of their container. The third bullet point, the time of collision is small compared with the time between collisions. The particles are moving randomly in all directions with a random range of speeds. The volume of the particles themselves is negligible compared with the volume of the container. Collisions between gas particles and the walls of the container are perfectly elastic. What does that mean? No kinetic energy is lost in the collision. And the forces between the particles are negligible. Forget about hydrogen bonding or anything like this in this idealized version of a gas. Now, if we had an exam question, I would suggest that it might be easier for you to remember one or two of the last three bullet points that I've highlighted in red. So, something that we do need to be aware of. Let's have a look at a few past exam questions. A football of diameter 22.5 centimeters contains air at a pressure of 1.65 times 10 to the power 5 pascals and a temperature of 20 degrees centigrade. Left in sunlight, the temperature increases to 40 degrees centigrade. What's the new pressure? Assume that the volume of the football remains constant. Indeed. New pressure? Well, we've got one pressure, we want another, we've got a temperature, we've got another temperature. P1 V1 over T1 equals P2 V2 over T2. The volumes are the same, so the volumes essentially cancel. And if we rearrange that, the new pressure, P2, equals P1 times T2 over T1. Put in the numbers, and we get 1.76 times 10 to the 5 pascals. Yes, it's an increase in pressure, and that's what we would expect from looking at the gas laws. We're asked to state another assumption. Well, we might say the air behaves like an ideal gas, or we might say that the number of air molecules doesn't change. Now, air is then slowly released from the football until the original pressure is reached. The temperature of the air remains at 40 degrees centigrade. We're asked to calculate the number of molecules that can escape. Which equation? Yes, PV equals NKT. But first of all, we need to work out the volume of the football. And the volume of the sphere is 4/3 pi r cubed. So we can work that out. And we know that N equals PV over KT. Well, we could do a rather lengthy calculation based on the original pressure, volume and temperature and the new pressure, volume and temperature. But a quicker way, if we look at that equation, is to say delta N equals delta P times V over KT. Because V isn't changing and T, the temperature, the absolute temperature, isn't changing. And if you look at my calculation, I've got the difference in pressure, which follows from my previous calculation. You might need to pause and go back for that. I've got the volume, I've got the Boltzmann constant, and I've put the temperature in Kelvin. Okay, and I get 1.52 times 10 to the 22 molecules. Fine. Next question. Explain why the pressure of a fixed volume of gas increases when the air is heated. Think about this for a moment. Isn't this going to be something to do with collisions of molecules? Yes. As the temperature increases, the kinetic energy of the molecules increases, they're moving faster. There are a greater number of collisions per second with the walls of the container. Now, please remember to put in per second, or to talk about the rate of collisions. But certainly the rate of change of the momentum will increase. And since force is proportional to the rate of change of momentum, from our impulse equation, impulse is force times time, which equals change in momentum. So F equals delta mv, change in momentum, over delta t, the time. So if the rate of change of momentum is increasing, that's delta mv over delta t, the force will increase and the pressure will increase, since pressure equals force over area. Worth remembering all of that. Okay, a New Scientist article says that an inflated balloon contains about 200 billion trillion air molecules. Oh gosh, how do we write that? Thankfully, it's written for us as 2 times 10 to the 23 molecules. Taking a balloon as a sphere of volume 8.2 times 10 to the minus 3 cubic meters at a temperature of 22 degrees centigrade. What is that in Kelvin? Show that the New Scientist article is correct. Well, we're told the pressure in the balloon as well. Okay, if we're talking about numbers of molecules, we're talking about PV equals NKT. So we need to change to Kelvin. N equals PV over KT. We've got the pressure, we've got the volume, we've got Boltzmann's constant, and we've got the temperature. So 2.2 times 10 to the 23 molecules, which is correct. Now, let's look at this. The New Scientist article states that the internal energy of the gas in the balloon could become zero if the temperature of the air became low enough. Explain what is meant by internal energy of the air and decide whether this statement is true. Well, if we're talking about the internal energy of a gas, we're talking about it as being the total potential energy plus the total kinetic energy. But for an ideal gas, molecules don't have potential energy. Forget about those stretchy bonds and the molecules boinging backwards and forwards. No potential energy in an ideal gas, only kinetic energy. So I'm saying here that the kinetic energy is EKE, and that of course is going to be proportional to the temperature. Again, this is something that we explore in the kinetic theory of gases. So the kinetic energy is directly proportional to the absolute temperature. And above absolute zero, the gas molecules are in continual random motion. If we're able to cool, and it's quite a technological problem, but if we're able to cool the gas to 0 degrees Kelvin, to absolute zero, or within a whisker of absolute zero, then there is no kinetic energy. The molecules stop moving. Yeah, and so the statement is correct. The gas will have no internal energy because all of that internal energy for an ideal gas is kinetic energy. Right, the graph shows the variation of pressure with volume. Pressure against volume. Perhaps this is representing Boyle's law, or Boyle's law experiment, or two. We're told that we're told that we've got two different fixed temperatures. That looks like A and B, two curves. The air behaves like an ideal gas. The number of molecules of air is constant. For curve A, the temperature of the sample is 25 degrees centigrade. Use the graph to determine the number of molecules in the sample. Oh my goodness, have I given you the answer there? Well, let's see how we get there. You can see that I've circled one point on graph A, where we know the temperature. We know the temperature, we change that into Kelvin, and for that point, we can read from the axes the pressure and the volume. The number of molecules, PV over KT, put in the numbers, and yes, we get 2.8 times 10 to the 30 molecules. Okay, job done. But the question doesn't stop there. We're asked to use the graph to determine the temperature of the sample for curve B. Well, we know P1 V1 over T1 equals P2 V2 over T2, and we already know P1 V1 and T1 P2 V2 and T2. Now notice that I'm assuming that we've got the same volume, 1 times 10 to the 5 cubic meters. So that's going to cancel on either side of the equation, and that's going to give us T2 is 544 Kelvin or 271 degrees Celsius. Let's keep going. When the sample of gas is cooled at constant volume, the pressure exerted by the air decreases as the temperature falls. Explain, using ideas of momentum, why the pressure of the air decreases. Now, this brings in some of the points that I was making earlier in the presentation. The average kinetic energy of a molecule is proportional to the absolute temperature. As the temperature decreases, the average speed decreases. So there are less collisions per second with the walls of the container. Again, we said impulse is force times time, which is change of momentum. So force equals delta mv over t, or force is the rate of change of momentum. So the rate of change of momentum for each collision will decrease as the temperature decreases. So there's a smaller force for each collision. Averaged over all collisions, pressure equals force over area. So if all these tiny forces of collision go down, the pressure will decrease. But hey, one of the things that's very important here is to talk about collisions per second with the walls of the container. Impulse equals force times time, which is change of momentum, and talk about the rate of change of momentum for collisions decreasing. That's very important to get full marks in a question. So you might want to have a look back at some of those calculations. That's Phys Physics, and keep working.